A qanāt is a gently sloping underground channel with a series of vertical access shafts, used to transport water from an aquifer under a hill. Qanāts create a reliable supply of water for human settlements and irrigation in hot, arid, and semi-arid climates. The qanāt technology is known to have been developed in Iran by the Persian people sometime in the early 1st millennium BC, and spread from the slowly westward and eastward. The value of the qanāt is directly related to the quality, volume, and regularity of the water flow. Much of the population of Iran and other arid countries in Asia and North Africa historically depended upon the water from qanāts. The areas of population corresponded closely to the areas where qanāts are possible. Although a qanāt was expensive to construct, its long-term value to the community, and thereby to the group that invested in building and maintaining it, was substantial. Etymology. Qanāt is the Arabic word for channel. Qanāts are also called kariz, kahan, kariz, keriz, katera, galaria, village, kana, fogera, thafara. Alternative terms for qanāts in Asia and North Africa are kakuris, chinavals, and mayan. Common variants of qanāt in English include qanāt, 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 qona, qanāt, garnet, qandat. Technical features. Qanāts are constructed as a series of well-like vertical shafts, connected by gently sloping tunnels. Qanāts tap into subterranean water in a manner that efficiently delivers large quantities of water to the surface without need for pumping. The water drains by gravity, with the destination lower than the source, which is typically an upland aquifer. Qanāts allow water to be transported over long distances in hot, dry climates without loss of much of the water to evaporation. The qanāt should not be confused with the spring flow tunnel, typical to the mountainous area around Jerusalem. Although there are similarities in the construction techniques, there are crucial differences between the two. Firstly, the origin of the qanāt was a well that was turned into an artificial spring. In contrast, the origin of the spring flow tunnel was the development of a natural spring to renew or increase flow following a recession of the water table. Secondly, shafts, which are essential to qanāts, are not essential to spring flow tunnels. It is very common in the construction of a qanāt for the water source to be found below ground at the foot of a range of foothills of mountains, where the water table is closest to the surface. For this point, the slope of the qanāt is maintained closer to level than the surface above, until the water finally flows out of the qanāt above ground. i.e., the qanāt is an underground tunnel, beginning from an underground water source, with a gentle slope made in such a way that water is pulled by gravity to the surface. To reach an aquifer, qanāts must often extend for long distances. Qanāts are sometimes split into an underground distribution network of smaller canals called kariz. Like qanāts, these smaller canals are below ground to avoid contamination. In some cases, water from a qanāt is stored in a reservoir, typically with night flow stored for daytime use. An ab-anbar is an example of a traditional qanāt-fed reservoir for drinking water in Persian antiquity. The qanāt system has the advantage of being resistant to natural disasters such as earthquakes and floods, and to deliberate destruction in war. Furthermore, it is almost insensitive to the levels of precipitation, delivering a flow with only gradual variations from wet to dry years. From a sustainability perspective, qanāts use the force of gravity to surface up groundwater with no energy requirement and, thus, have low life cycle operation and amp maintenance costs once built. Qanāts transfer fresh water from the mountain plateau to the lower-lying plains that have a saltier soil. This helps to control the salinity of soil and prevent desertification. features common to regions that use Qanāt technology. The Qanāt technology is used most extensively in areas with the following characteristics: an absence of larger rivers with year-round flows sufficient to support irrigation, proximity of potentially fertile areas to precipitation-rich mountains or mountain ranges, arid climate with high surface evaporation rates so that surface reservoirs and canals would result in high losses, an aquifer at the potentially fertile area which is too deep for convenient use of simple wells. Impact of qanāts on settlement patterns. A typical town or city in Iran, and elsewhere where the qanāt is used, has more than one qanāt. Fields and gardens are located both over the qanāts a short distance before they emerge from the ground and below the surface outlet. Water from the qanāts defines both the social regions in the city and the layout of the city. The water is freshest, cleanest, and coolest in the upper reaches, and more prosperous people live at the outlet or immediately upstream of the outlet. When the qanāt is still below ground, the water is drawn to the surface via water wells or animal-driven Persian wells. Private subterranean reservoirs could supply houses and buildings for domestic use and garden irrigation as well. Further, airflow from the qanāt is used to cool an underground summer room found in many older houses and buildings. Downstream of the outlet, the water runs through surface canals called jubs which run downhill, with lateral branches to carry water to the neighborhood, gardens and fields. The streets normally parallel the jubs and the lateral branches. As a result, the cities and towns are oriented consistent with the gradient of the land. This is a practical response to efficient water distribution over varying terrain. The lower reaches of the canals are less desirable for both residences and agriculture. The water grows progressively more polluted as it passes downstream. In dry years, the lower reaches are the most likely to see substantial reductions in flow. Construction. Traditionally, qanāts are built by a group of skilled laborers, mekanis, with hand labor. The profession historically paid well and was typically handed down from father to son. Preparations. The critical, initial step in qanāt construction is identification of an appropriate water source. The search begins at the point where the alluvial fan meets the mountains or foothills. Water is more abundant in the mountains because of orographic lifting, and excavation in the alluvial fan is relatively easy. The mekanis follow the track of the main watercourses coming from the mountains or foothills to identify evidence of subsurface water such as deep-rooted vegetation or seasonal seeps. A trial well is then dug to determine the location of the water table and determine whether a sufficient flow is available to justify construction. If these prerequisites are met, the route is laid out above ground. Equipment must be assembled. The equipment is straightforward: containers, ropes, reels to raise the container to the surface at the shaft head, hatchets and shovels for excavation, lights, spirit levels of plumb bobs and string. Depending upon the soil type, qanāt liners may also be required. Although the construction methods are simple, the construction of a qanāt requires a detailed understanding of subterranean geology and a degree of engineering sophistication. The gradient of the qanāt must be carefully controlled. Too shallow a gradient yields no flow, and too steep a gradient will result in excessive erosion, collapsing the qanāt, and misreading the soil conditions leads to collapses, which at best require extensive rework and at worst fatal for the crew. Excavation. Construction of a qanāt is usually performed by a crew of 3 to 4 mekanis. For a shallow qanāt, one worker typically digs the horizontal shaft. One raises the excavated earth from the shaft and one distributes the excavated earth at the top. A crew typically begins from the destination to which the water will be delivered into the soil and works toward the source. Vertical shafts are excavated along the route, separated at a distance of 20 to 35 meters. The separation of the shafts is a balance between the amount of work required to excavate them and the amount of effort required to excavate the space between them, as well as the ultimate maintenance effort. In general, the shallower the qanāt, the closer the vertical shafts. If the qanāt is long, excavation may begin from both ends at once. Tributary channels are sometimes also constructed to supplement the water flow. Most qanāts in Iran run less than 5 kilometers, while some have been measured at 70 kilometers in length near Qanāt. The vertical shafts usually range from 20 to 200 meters in depth, although qanāts in the province of Khorasan have been recorded with vertical shafts of up to 275 meters. The vertical shafts support construction and maintenance of the underground channel as well as air interchange. Deep shafts require intermediate platforms to simplify the process of removing soil. The construction speed depends on the depth and nature of the ground. If the earth is soft and easy to work, at 20 meters depth a crew of 4 workers can excavate a horizontal length of 40 meters per day. When the vertical shaft reaches 40 meters, they can excavate only 20 meters horizontally per day, and at 60 meters in depth this drops below 5 horizontal meters per day. In Algeria, a common speed is just 2 meters per day at 15 meters depth. Deep, long qanāts require years and even decades to construct. The excavated material is usually transported by means of leather bags up the vertical shafts. It is mounted around the vertical shaft exit, providing a barrier that prevents wind-blown or rain-driven debris from entering the shafts. These mounds may be covered to provide further protection to the qanāt. From the air, these shafts look like a string of bomb craters. The qanāt's water-carrying channel must have a sufficient downward slope that water flows easily. However, the downward gradient must not be so great as to create conditions under which the water transitions between supercritical and subcritical flow. If this occurs, the waves that result can result in severe erosion that can damage or destroy the qanāt. In shorter qanāts, the downward gradient varies between 1 to 1000 and 1 to 1500, while in longer qanāts it may be almost horizontal. Such precision is routinely obtained with the spirit level and string. In cases where the gradient is steeper, underground waterfalls may be constructed with appropriate design features to absorb the energy with minimal erosion. In some cases the water power has been harnessed to drive underground mills. If it is not possible to bring the outlet of the qanāt out near the settlement, it is necessary to run a jubber canal overground. This is avoided when possible to limit pollution, warming and water loss due to evaporation. Maintenance. The vertical shafts may be covered to minimize blown-in sand. The channels of qanāts must be periodically inspected for erosion, the cave-ins cleaned of sand and mud and otherwise repaired. For safety, airflow must be assured before entry. Restoration. Some damaged qanāts have been restored. To be sustainable, restoration needs to take into account many non-technical factors, beginning with the process of selecting the qanāt to be restored. In Syria, 3 sites were chosen based on a national inventory conducted in 2001. One of them, the Dressar Qanāt of the was completed in 2002. Selection criteria included the availability of a steady groundwater flow, social cohesion and willingness to contribute of the community using the qanāt, and the existence of a functioning water rights system. Applications of qanāts. irrigation and drinking water supply. The primary applications of qanāts are for irrigation, providing cattle with water, and drinking water supply. Other applications include cooling and ice storage. Cooling qanāts used in conjunction with a wind tower can provide cooling as well as a water supply. A wind tower is a chimney-like structure positioned above the house, of its 4 openings. The one opposite the wind direction is opened to move air out of the house. Incoming air is pulled from a qanāt below the house. The airflow across the vertical shaft opening creates a lower pressure and draws cool air up from the qanāt tunnel. Mixing with it, the air from the qanāt is drawn into the tunnel at some distance away and is cooled both by contact with the cool tunnel walls, water, and by the transfer of latent heat of evaporation as water evaporates into the air stem. In dry desert climates, this can result in a greater than 15 degrees Celsius reduction in the air temperature coming from the qanāt. The mixed air still feels dry, so the basement is cool and only comfortably moist. Wind tower and qanāt cooling have been used in desert climates for over 1,000 years. Ice storage by 400 BC, Persian engineers had mastered the technique of storing ice in the middle of summer in the desert. The ice could be brought in during the winters from nearby mountains, but in a more usual and sophisticated method. They built a wall in the east-west direction near the Yagchal. In winter, the qanāt water would be channeled to the north side of the wall, whose shade made the water freeze more quickly, increasing the ice formed per winter day. Then the ice was stored in Yagchals, specially designed, naturally cooled refrigerators. A large underground space with thick insulated walls was connected to a qanāt, and a system of wind catchers or wind towers was used to draw cool subterranean air up from the qanāt to maintain temperatures inside the space at low levels, even during hot summer days. As a result, the ice melted slowly and was available year-round.